Now let's talk about this Hottel's cross-string method. Now, even though some equations exist and some graphs exist in solving for the view factor, there are also cases when 2D objects, so I would have to specify that this is applicable for 2D planes only, or 2D figures, in such a way that we can draw strings. So this is also an easy way, but sometimes it becomes very difficult. But you can do string method to calculate for the view factor of the two materials. Usually we employ two materials that are relatively at a distance with each other, and then they are actually symmetric or equal in area. But not in all cases so we'll be doing that. So now let's try to do the Hottel's cross-string method in this figure. So what I have here is these are two circles with a diameter of 33.02 mm, and then they're separated by a distance of 59.61 mm center to center. So we need to find Fij, meaning we need to find the view factor, that is, the radiation emitted by I received by J. So what could probably be the view factor for Fij? Now, to evaluate this Hottel's cross-string method, we have to understand what we mean by string. So this string is actually an imaginary line that we draw as if they are strings pinned from the edge of the objects. So for example, I have a pin. Let's have the strings in color blue. So I try to add some pin here. So this is my object 1. I'll be starting with I, and then I will try to draw string. So in this case, the first string I will draw would be starting from this. Let me just make it straight. So now the first string that I'll be drawing is from this pin, and then I would draw a string that would connect this other circle. So the next one would be, I'll be pinning from this, and then I'll be drawing another string here. So in that way, that looks symmetric. And let me just add some letters here just so that we can pinpoint location. So we have A and then B, and then at this point is, let's say, C and then D. Okay, and by doing the edge-to-edge string, I also have to add another string that connects the diagonal. So in this case, if I will be drawing a diagonal here, we could see that I can connect these two pins. But remember, in Hottel's cross-string method, we have to account the shape of the figure. So if I'll be drawing a diagonal that transcends these two circles, I would have to like stop somewhere here so that the string won't, it won't get passed through this figure. It's just that if you would imagine a string and then it starts from this point, I would have to like trace this curve first so that I can proceed with this one and then trace this curve again. So in this case, the diagonal won't be exactly as if it's the connection of these 2 points, but rather it is something like it traces something like the circle first, and then so that it can cross through that pin. So in this case, I need to have this cross first and then take tangent, the line that will be tangent to this point, going through this line, and then somehow I would also this, it's like I'm trying to get the tangent line, and then the rest of it being the point of tangency is here, and then I would try to like draw an arc so that I can get right through there. And then there's also this tangent point here, and then I will also trace this small curve from here. So that's the string of A. So let's have the tangency here. We have E, that's the point of tangency, and there is F. So it's like we have a curve AE added with EF plus the curve of FT. So that's the string that comes from this pin. It's the same thing for C. We trace the curve on here and then we take the line that could be tangent with these two. So that's the diagonal that is tangent between this, and then we trace the remaining curve. So in this way, we could see that this is perpendicular. If we would like to trace something like, let's try to use a different color. So if we would try to draw something from here, we know that this is from the center. It's like the radius distance. This is tangent to the line, and that's the same way it goes for this one. So it's tangent. So this is also tangent. This, okay? And Hottel's cross-string method states that if we have something like the view factor, we can determine it by using the formula. Let's say we have IJ material, so we can determine the view factor of IJ by taking the total cross string. So if you take the sum of the lengths of the total cross strings and then subtract it with the total uncrossed, and then divide it by the total area, which is the original area, we can obtain the view factor. But if, of course, if we need to simplify this further, we can say, and usually in symmetric objects, we can say that Fij is simply the diagonal, because if the diagonal would be the same, then that's just saying that we have two diagonals here and then two sides, because we usually refer to the uncrossed strings as sides, and then we have here the two area. And area here doesn't actually mean that it is area like the dimension is meter squared, but the area, circumferential area if it's circle, and the arc length if they are just the hemisphere. So it's like that. It's like the perimeter that is in concern. We're just referring to that as area because we usually refer to this as the surface. So if that's the case, then we can cancel this out and we're left with the formula of Ij, that is one diagonal and then subtract by one side and then divide it by the area. So in this case, let's solve for the first one here. So I've already drawn the strings. Those are in the blue one. And what we need here is to find the diagonal. So that's the cross string. So in here, the diagonal or the cross strings are this one. They actually crossed. The C, let's just name this so that, let's name the diagonal. So that's AE. So the arc AE with the distance going to EF plus, so that's the segment, and then arc FT. So that is our crossed string. So that's one. So we need to find that the length of this, so that we can consider this as the diagonal, but it's not exactly the diagonal but the cross string. And then our side would be the string that didn't cross. So that's simply the distance between A and C. And if we would take a look at the distance of A and C, we can actually see that this is the center to center distance of Ij, that is also equal to BD. And this is equal to 59.61 mm. So in this case, we already have the side. We just need to find this cross string. And by the way, the area would not be the area of the circle, but the circumference of this circle where our string originated. So we originated from I, so the area would be equal to pi d, and that is the diameter, which is 33.02. So now let's try evaluating this, given that we already have the value of this. Let me just write 33.02 and then that's pi mm. So we already have this side area, and then we just need to find the cross string. So the cross string, if you would take a look at this, we just need to find the distance from here and then the arc length. Now, to find EF, because that's the easiest one here, we could actually draw some triangles here. Now, if we would imagine drawing something like a line here, so I'll be drawing a line here, and actually the diagonal should have crossed this, but I didn't draw the correct diagonal, so it didn't cross, but technically it should have crossed this line just to see that they form a triangle. So that's typically how it looks, and you see this one as a right triangle. So if that's a right triangle, we could say that this is a right angle. So we could say that this one is a right triangle. And since this one is a bisector, this line here that is the center to center line is a bisector of this diagonal, we could say that these two are actually equal. And what we need to do is to find this value here, the EF. And to do that, let's try to find the value of this midpoint or midway EF first. So from the figure, I can just take out this triangle here so that you can see it clearly. So this is the 90 degrees and then this is the angle. So as you can see here from the figure, we could see that this is the center to the midway or the center distance between these two figures. So in that case, if that's 59.61, I can just take the half of that, and that will be the distance of this triangle. And then knowing that this is the center to a certain point at the circumference, that will mean that it is the radius of our circle. So I can also give the value of this length, which is 1/2 of 33.02. So in this case, I now have taking this, let's say this is theta. So this is theta. I will now have the opposite value for the dimension of the triangle for theta, and of course its hypotenuse for this triangle. So in this case, let me just give the values for this. So this one is equal to 29.805 mm, and this one is equal to 16.51. So now that we have the values of our the two legs, what we need here is the value of this side here, and let's just name that as S. So this S here would mean that if we have 2S, that is actually equal to the distance between E and F. Okay, so if that's the case, I just need to find S here from this figure. Now, to find S, we can actually use sine law or cosine law or whichever law is applicable. And the easiest way that we can do this is to find theta. So if I will be finding theta, I can just take out theta here, and we could use the relationship for sine, because the sine of theta is actually equal to the opposite over the adjacent sides. And in this case, that's 16.51 divided by 29.805. So in this case, theta will be the arc sine of that value, and I will be getting that is 0.5871 in radians. So to be able to get this S, that is simply equal to the S, or the length from E midway to F, would be equal to the cosine of theta, because that is the adjacent one, and of course we need to multiply that with the hypotenuse, so that is multiplied with 29.805. So in this case, this is equal to cosine of this angle and multiply with 29.805. So in this case, S would be equal to, therefore S is equal to 24.8145, and that is in millimeters. But since I need here 2s, so 2s is equal to twice this value, so I have now 49.6289 mm. So this is equal to the distance between EF. And we're not yet done, since we've already determined the EF, but we need to find the distance between the arc AE. So this arc AE, of course, is a continuation of the string that we actually used to draw from the pins that we did for these two figures. So in this case, I need to find AE, and to do that, we need the angle for this, which is, let's call it alpha. So if I call this alpha, I need to determine this angle from all the things that we did here. Now, if you look at here, if we would like to extend our triangle here, we could see it from here that it goes past this circle. But the idea here is that if we would try to extend here and take this as our alpha, we could see it from here that we have formed this triangle as if they are similar, or something like it gives us the idea of similar triangles. And knowing that this is the perpendicular angles for this triangle, and since this is alpha, we could see it from here that this forms also 90 degrees. And knowing that this is 90 minus this theta, we could also tell from this inspection that the value of this angle here would be equal to something like alpha plus 90 minus theta is actually equal to 90. And therefore, if we would cancel this out, we could see that theta would be equal to alpha. So by similar triangles, we could see here that the alpha that we need to find here is actually equal to the value of our theta. So in this case, let's use theta to find to find the arc length, which is AE. So I'll be using another color. So the arc length of AE is actually equal to that's simply r and then theta. So that's how it goes for our arc length. So we have AE, that is, the radius is 33.02, that's 16.51, so that's 16.51 mm, and then theta, so that's 0.5871. So we don't have to like convert this anymore to radians since it's already converted. So the answer using this value would be equal to 9.6927 mm. So in this case, the arc length is 9.6927 mm. Well, but there's also this FD, which is the same length for AE, and we need to add that to our string. So if we need the value of our cross string, finally we need to take FD from this figure. So we have FD. So FD is also equal to 9.6927. Therefore, our cross string. So let's have the cross string is equal to 2s, which is the EF. So that's 49.6289, and then 2 of this arc length. So we have 9.6927 times 2. So our cross string is actually equal to 69.0144 millimeters. So knowing the cross string and its value, we can now substitute that to our formula, which is this one. So Fij, is equal to 69.0144, and then subtracted with the total uncrossed. So the total uncrossed is simply this 59.61. So we have here 59.61, and then this is the circumferential area, so that's pi, and then we need to like multiply this with the diameter, so that's, I think it's 33.02. Yes, it's 33.02. So that is 33.02. So with that, the view factor of Fij is equal to 0.0966. So we don't have any unit for this. So that is the view factor for this figure. That's 0.0966. So I hope you understood how this works for the derivation of the strings. It's kind of messy because there are a lot of figures and graphs. But in the Paris handbook, you could see a simplified form of this cross string. So let's head over to this chapter. This one, the cross string method. So there's an explanation here, and this is how it's done for the direct exchange for parallel circular tubes, and this is the shortcut of this value. And if you'll be evaluating that using the same example that I've given you, then you'll be able to find the same answer, that is 0.0966. So that's a shortcut way, but if you don't know how it is derived, or if you're just wondering how this Hottel cross-string method is used, or employed in a way that you use conventional method, then you can just use this method. Just draw strings and you're done. But the difficult part here is just finding the length of the string. Okay, so we're done with the first example. Now let's try the one that you can see here below. So in this case, we don't have any figure that is the same. So it's a different figure. It's a semicircle, and then there's a plate above it, and we need to find Ij. So we need to find the radiation that is sent by I, that is intercepted by J. So what will be the view factor of Fij? So we'll be using the same formula again. That is Fij is equal to the diagonal minus the sides, or the side, and then divided by the area of origin. So in this case, since we're talking about Ij, we'll be pinning from I. So we'll be pinning from this circle. Now I want you to pause the video and try to draw this crossed string, so that you might have an idea of how this works. And then go back here after you've drawn and check it if you've already pinned and stretched the correct strings. Okay. Now let's try pinning some strings here. I would start with I, since this is the figure of origin. So I'll be drawing some pin at the edge, and then I will draw a pin that goes through the edge of this plate. And I'll do the same thing for the other edge. So let's have something like A and then B here, just to name the string. So A to B is the string that is at the side, and you can see here, it's already the uncrossed string. So I can also take this string, and then I would pull a string up to here in a way that I can connect that to the opposite side of this, and then that's the same thing as this one, and I'll be pulling that string up to the corner. So in this case, the crossed string would be this, and then we do have something like this. At a point somewhere here, it traces the curve, so in that way it doesn't something like it goes straight to that pin. So at this point, we could see here that, let's have a name for this, let's say C, and in that point we could notice that we can draw something like a line here, and that will be perpendicular with that radius. Now, the only difficult thing to find here is what could be the distance from B. Probably, let's say we have something like, let's name it, this point is D. This point, let's say it's E. And then let's have a point here that's F. So the only difficult part here is to finding the distance between D going through C. And because that's not a straight line, we should be adding CA. So the cross string, I'll just be taking one string. So the cross string would be equal to the distance between DC, so that's the whole thing here, and then the one that is the arc length of CA. So that is our cross string. And then the side, or the uncrossed string, we have here the distance between BA. And of course, the area, or our circumferential area in this case, would be pi over 2 times the diameter. So let's just use small d. So we can give the value of this, so that's pi over 2, and then the diameter is actually equal to 18.44 over 2. So we have so we can have 4.61 pi. So that is our area, since it is not pi d, it's pi over 2d because it is a semicircle. So let's head into the side first, because as you can see here, the side is easier to be solved. Why? Because if you would look closely at this BA, we could see here that this one is BA, and then knowing that this is the plate that is there and this semicircle is directly below the 61.13, we could see that the distance from the edge going through this side to the center of the circle would be something like the midpoint of 61.13. So now if we'll be projecting that line through this figure, we could see it from here that this is the distance from this point going to the center of the circle, and that's half of 61.13, so that's 30.565 mm. And knowing that this is 30.565, and knowing that this is also the radius of this, this semicircle, we could actually find the distance between this by subtracting 30.565 by the radius of the circle. So in that way, I have 18.44. What's left here would be 12.125. So this distance is 12.125, and this one here is actually given, that's 36.69. So therefore, BA by Pythagorean theorem is actually equal to the square root of 12.125 squared, this one, plus the square of 36.69. So therefore, the distance between BA is equal to 38.6416. So this is our side. And to countercheck that by inspection, we should be having a value that is greater than this 36.69, because that's actually the hypotenuse. And knowing this side, we need to find now the cross string. And this one is a more complicated version of this form, but if we will try to look closely at the geometrical figures that will be formed, then it will be easier for us to solve it. Now from this figure, we can draw a triangle that is tangent to the semicircle, so that we can derive the equation for similar triangles. So in this case, I'll be doing something like these lines to create a triangle. So let's name some of the points here. So the new point that is right here just beyond the imaginary line, let's have this as G, and then this point at the very center of the circle, let's have it as H. Now that we've drawn the figure, let's take it right here so that we have some clearer view of the triangle. So we have here the triangle, and then here is that radius that is perpendicular. So if we name this angle as alpha, and then this one is theta, so we can therefore say that this one is also theta. And we're already given with the value, which is 36.69. So this is the value for that leg. And then this one, if we would look here, we could see that at the edge of this plate through the center, that is, we've already solved for that, and that's 30.565. So we can use that to give the value for this. So that's 30.565 mm. And through here we don't have any value, so let's name that as x. And to the point of this hypotenuse, we could see here that let's have some C here, and then D, and then G, just being consistent with the naming here. So to use the similar properties of triangles, because as you can see here, it is one leg is drawn perpendicular to its hypotenuse, so we can use the property of similar triangles. We could see here that the one leg here, which is 36.69, we divide that by the long leg, so that's x plus 30.565. That should be similar to the same the corresponding legs that we have. So if this is theta, if this is the alpha, we need to take the leg that is opposite the alpha. So this is that leg, and this one is actually the r, which is 18.44. And finally, since we need to take the side that is opposite theta, so in this smaller triangle we can see that that is CG. But CG is actually equal to the square root of x squared minus 18.44, knowing that it is also a right triangle. So in this case, if we would be solving for x, we can therefore find that the value of our x is 39.9507. So this is the value of our x, and to be able to find CD, which is the thing that we need here, we need to find CD, we just need to find this DG, which is the hypotenuse of the bigger triangle, and subtract this CG from that. So the hypotenuse would be, we'll be using this x to find the hypotenuse. So in this case, we have 39.9507, and we add that with 30.565 to get the longer leg of the longer triangle, or the bigger triangle. So we square that and then add the square of the other leg. In this case, this is the hypotenuse of the bigger triangle. Then we subtract the leg of one of the smaller triangles. So in this case, we have the square root of 39.9507 squared, and then we subtract 18.44 from that, then squared. So we get now the value of CD. So the value of CD is equal to 44.0493. And in this case, since this is our CD, we can now find the value of our theta, because we need to find the arc length to finally determine the value of our cross string. So in this case, CA would be equal to R times the angle theta here, because as you can see here, theta would mean that you will traverse this circumferential length, or that arc, through the angle which is theta. So we just need to find theta, and To do that, let's have some trigonometry background again. So if this is theta and this one is the adjacent to that angle and this one is the hypotenuse, we could simply use this cosine of theta to give us the value of cosine. So we could just use this cosine theta to give us the value of our theta. So that's simply the adjacent over the hypotenuse. So in this case, cosine theta is equal to the adjacent, which is dr. That's 18.44, and our hypotenuse is simply the x value, so that's 39.9507. So therefore, taking this arc cosine of this value, we get 1.0910. So this value, if you would like to convert this to in degrees, so that we can have an idea, that's around 62.5096 degrees. So we can use that theta to continue solving. So we have r, that is 18.44, and then we have 1.0910. So our arc length CA is equal to 20.1187. So now that we already have the CA, we can now add them so that we can have the value of the crossed string. So the cross, let's have some this. So the cross string is equal to 20.1187 plus we have 44.0493. So the value of our cross string would be equal to 64.168. That's 64.168. And finally, to get Fij, we have to input all the values, 64.168, and then subtracted with this side 38.6416, so that's 38.6416 all in mm, and then divide this by the area, which is actually this should be since this is the diameter and 18.44 is actually the radius, we can it should be something like 18.44 times 2. Sorry, my bad. So that should be the diameter, and then we divide it by 2, so we cancel this and we're left with this 18.44 pi, which is the semicircle. So let's erase this. So we have 18.44 pi. So this means that we have the r pi, which is simply the half of the supposed diameter. So we have 18.44 pi. So this is equal to 0.4406. So this is our value for the view factor of Ij. Okay, so we've done that using the crossed string method. So remember, this cross string method actually employs a lot of mathematics. So if you'll be using this, you should always review your math, especially in geometry. So with that, we're down to the last two problems, and let's try this one.